if we open up this, we'll have cx squared, and on the other side, the only place having x squared has a coefficient of 1. So that coefficient 1 tells us that a plus c must be equal to 1. Our coefficient for x square on the right hand side must be equal to our coefficient for x square on the left hand side. So in essence, a plus c are the ones attached to x square on the right hand side, and so their sum must be equal to 1 because our coefficient of x square on the left hand side is 1. And so 1 is equal to a plus 5 over 9. We've gotten c before to be 5 over 9, and so a is 4 over 9. We'll substitute all that into our initial breakdown, which was a over the first factor plus b over the repeated linear factor plus c over the second factor, and that's what we have. So a is 4 over 9. We'll divide it by x minus 1 plus b, we got 2 over 3 into x minus 1 squared plus c, which is 5 over 9 divided by x plus 2. To the third case, we have irreducible quadratic factors. As we can see in the example, 10 over x minus 1 into x squared plus 1. At the denominator, we have a linear factor and a quadratic factor. And the quadratic factor is irreducible, so we can't get any repeated linear factor from that quadratic factor. Once we have come to that conclusion, then we go by this procedure. Our fraction, which is the problem we are given, will now be decomposed this way: a over the first factor, or over the linear factor you can find, plus bx plus c. Bx plus c is like a general form for a linear expression. Bx plus c over the irreducible quadratic factor that you are seeing. So that's the format. A will be over the linear factor, bx plus c will be over the irreducible quadratic factor. And so next we'll apply LCM. The LCM will be this, which is the same denominator we're having on the left hand side. If you use that LCM to multiply each of these terms, we'll get a new numerator, and so our numerator on the left hand side, which is 10, will be equal to a new numerator, a into x squared plus 9 plus bx plus c into x minus 1, like we have here. Next, we start substituting values for x that can eliminate each of the factors and give us solutions for the other factors. If we substitute x equals 1, of course b and c will be eliminated, because x equals 1 here makes all this 0, and so we'll get a value for a. When we do that solving, we'll have a equals 1. If we equate coefficients like we did in the previous example, equating coefficients for x squared, you see that on our left hand side there is no x squared term, so that it implies that our coefficient for x squared on the left hand side is 0. And so, but on the right hand side, if we expand, we have ax squared a will be one coefficient, then bx here times x here will give us bx square. So we have ax square plus bx square. We factor out x square, we are left with a plus b. So a plus b is a coefficient for x square on the right hand side, and so we are saying that a plus b must be equal to 0, because on the left hand side we have no coefficient for x squared. If that's the case, we already have a to be 1, and so if a plus b must be 0, then b must be minus 1. Next, we have constants on our left hand side. 10 is the constant term there, attached to no variable, so it's constant. On the right hand side, we have c standing alone as a constant, right? But then there might be other cases which we are going to check, where some of these letters are standing alone. So let's see. In this expansion now, a we multiply 9, and we have 9a. 9a is a constant, it's not attached to any x. Same thing here, c, at the end of the day we multiply this minus 1, we have minus c, and so those are all the constants we can find. We have 9a minus c equals 10. When we solve that, we already have a value for a, which is 1. C then will become minus 1. Plug in everything to this general decomposition format, and we have our problem. 10 over x minus 1 into x squared plus 9 will now become 1 over x minus 1 minus x plus 1. We're having x here because b is minus 1, and that is this minus. That's changed our plus to minus. Minus x plus 1. This is plus 1 because c is minus 1. Minus, this minus covers the whole x plus 1, and all over x squared plus 9. Now to the final case. Case of an improper fraction, that is, the degree of the polynomial in the numerator is higher than the degree of the polynomial in the denominator. We have to do this polynomial long division. That is, we divide the numerator by the denominator to have a new to be able to represent the improper fraction as mixed numbers, that is, a whole polynomial that will stand for the whole number plus a proper fraction. And before we now decompose that proper fraction, now to represent our improper fraction, we'll start by dividing the highest degree, the term where in our numerator where our variable is carrying the highest degree, that's x cubed. We'll divide it by the term in our denominator where the variable is carrying the highest degree, which is x squared. So x cubed divided by x squared gives us x, and so to get the remainder, we would multiply that x that we've gotten from our division by the denominator, which is x squared minus 4, That gives us x cubed minus 4x. Then we subtract this x cubed minus 4x from the original numerator. That gives us the original numerator is x cubed plus 2x squared minus 1. Then minus this x cubed minus 4x. That now gives us 2x squared plus 4x minus 1. That is the remainder from the first step of our division. And you can see this 2x squared plus 4x minus 1 is not yet, is a polynomial, but the polynomial is not yet in a degree that is less than the degree of our denominator. They are on the same degree now. We need to reduce it to a degree that must be less than the degree of the denominator. And so we'll take the highest again, the same procedure, which is 2x squared. That's the term carrying the highest degree. That 2x squared divided by x squared, that's the highest degree in our denominator. 2x squared divided by x squared will be left with 2. So take note of these two results we have gotten from our divisions so far. We've gotten x, we've gotten 2. So we'll keep adding them to each other. So these 2 that we've gotten now, same procedure, we'll multiply it by the denominator, 2 times x squared minus 4. That gives us 2x squared minus 8. We'll use that now to get our remainder by subtracting from the numeric and the previous remainder. So that will be 2x squared plus 4x minus 1 minus this 2x squared minus 8 will have 4x plus 7. Now our new fraction is now x plus 2 plus 4x plus 7 over x squared minus 4. We have been able to represent our improper fraction, which we were given in the problem, as a new a polynomial plus a proper fraction. Now you can see that 4x plus 7 is in a lower degree to x squared minus 4. Now take note, x squared minus 4 is a difference of 2 squares, and that can be rewritten as x minus 2 into x plus 2. So looking at this case, this looks like our case 1, a linear factor over 2 linear factors. When we solve, next step here, we'll do LCM and then start eliminating. Of course, we want to have 2 fractions. That will be a over the first factor, x minus 2, plus b over the second factor, which is x plus 2. And when you do all that, you will have a to be 15 over 4 and b to be 1 over 4. That is when you do LCM and you start eliminating. You eliminate a, you substitute a value for x that will eliminate a, substitute a value for x that will eliminate b. At the end of the day, a will be 15 over 4, b will be 1 over 4. And so the final result is x plus 2 plus 15 over 4 over x minus 2 plus 1 over 4 over x plus 2. That brings us to the end of partial fraction decomposition. I'll be taking your questions in the comment section. Thank you.